Welcome, ladies and gentlemen. So does the mean value theorem apply to the function f of x equals the cube root of x on the interval 0 to 8? Well, recall that my function needs to be continuous on the closed interval 0 to 8 and differentiable only on the open interval. And so even though y equals the cube root of x has a vertical tangent at x equals 0, the requirement for the mean value theorem is only that we have continuity at the endpoints and differentiability in between them. So we've got a strictly for the open interval, and so we're fine for applying the mean value theorem, which means that we can find some x equals c value where the instantaneous rate of change, that is the slope of the curve anywhere along it, is equal to the slope of the secant line connecting the endpoints. That is the average rate of change over the interval. F at b minus f at a all over b minus a. Graphically, we've seen this before. We know we're talking about some function that's continuous and differentiable over an interval. There has to be some place where the slope of the tangent to the curve is the same as the slope of the secant line to the curve. So here we've got my f at a, my f at b, my a, my b, and the graphical representation thereof. So here's my slope of the secant line, right, that we could calculate. Here's my slope of the tangent line. And we're going to see where that happens for this particular function on my interval 0 to 8. So what do we need? Well, we have a, we have b, we need f at a and f at b. So I'll go to my original function. It looks like f of 0 is 0. F of 8 is cube root of 8, that's 2. So my average rate of change calculation is 2 minus 0 all over 8 minus 0 equals 1/4. Raise your hand if you have 1/4 for the slope of the secant line, the average rate of change interval. Great. What do I want to do? Well, I want to find the particular x equals c value in between 0 and 8, where the instantaneous rate of change, synonymous with derivative, is equal to the average rate of change. Let's do it. So what do I need? Well, I need f prime. We'll generate f prime by using the power rule. F prime of x is given by exponent times the base raised to 1 less. Times the derivative of the base is just 1. So it looks like we need to set this equal to my 1/4 that we calculated and see if we can solve. What? Well, I think we can solve this, right? We'll have to use the exponent theorem. To undo an exponent, we can raise both sides to the reciprocal exponent. But in order to do that, we need to first isolate my power. So the best first step is not to do any exponent raising. It's to multiply both sides by 3, yes? So we'll clear that. We'll get that power function isolated by multiplying the 3 over, and I get 3/4. Then we can purposely undo that current exponent by raising each side to the reciprocal exponent. Now, you could have rewritten this so you had positive exponents or multiplied over, or however you wanted to handle it, solving algebraically. I think it's quickest here just to raise both sides to the negative 3/2, and then worry about my simplification later. So negative 3/2, negative 3/2, go to gadget arm. I'm getting x equals 3/4 to the negative 3/2. Now, that doesn't look very pretty, and I have no idea if that's in my interval or not. And so what can we do? Well, we can apply my properties of negative exponents. I know that negative exponents don't mean negative answer, they mean reciprocal. And so 3/4 to the negative 3/2 is the same as 4/3 to the positive 3/2. And 4/3 to the positive 3/2 looks like the square root of 64. Go gadget arm. The square root of 64 27ths. Is that right? 3 cubed is 27? All right. So I have no idea what that is, but we're going to go ahead and check graphically, and I'm going to do my second calculate dy dx. Square root of 64 27ths, and see if it jumps on the curve and spits out a derivative value that is 1/4. Let's try it. So I'll go ahead and go to my calculator, and I'll get my y equals cleared out, and I wanted the cube root of x. Uh-oh. Math 4. Uh-oh. Ah, very nice. X, and we'll set my window maybe -1 to 9, and maybe -1.5 to 3, and we'll see how that works. Here comes my cube root function. And graphically, I know I'll find found the correct C value if the calculated derivative value approximation is 1/4, right? So how do I do that? Well, I can do second, calculate, and my particular x value of concern that I found is that right? The square root of 4 cubed is 64/27, yes? So I want the square root of 64/27. Pinch of salt over the shoulder, right? And we'll see what happens. Ready to go. No good. 1.1. Oh, that's the y value. The dy dx anticipated value is 0.2500000002. So my calculator is giving us the old college try and trying to tell us 1/4. Math works. That's very sweet. I'm dying to know. Sorry, at this stage. So who generated 4/3 to the 3/2, or the square root of 64/27 is good. So we find the slope of the secant, we find the derivative, we set the derivative equal to the slope of the secant, solve. So we did the same process in lesser, right, in lesser complexity back in AB. Now a little bit more complicated with our stuff, but still should be go-to. We need the mean value theorem for our optimization strategy we'll be looking into next time. All right, so what questions do you guys have about today's Bellwork? Awesome. Then let's go ahead and pause the recording and get going on our check. Awesome. So today we're going to do a quick introduction activity. This activity probably won't take very long, but there are the 3 stamps, right, that you can earn. After you get your 7B stamp, right, we're going to come back together. We're going to take a look at some graphing examples together, where we're going to step back from our comfort zone without our graphing calculator, and we're going to take a look at some more complicated examples than you've seen up until this point. After that, we'll take care of our closure, and you might have a chance to do our to get started on your OTL number 2. And it's good to have a goal. So I'm going to go ahead and pause the recording. Let's scooch into our groups and investigate the connection between a function and its derivatives. Okay, ladies and gentlemen, let's go ahead and take a look at how we can apply our first and second derivatives, y prime and y double prime, respectively, to analytical graphing with our knowledge of function behavior. So let's go ahead and take a look at our first example. We're going to use analytic methods to determine the intervals of increasing versus decreasing behavior and any local extrema. Then we'll verify graphically using our graphing calculator, but we're going to do it all without a calculator first. So what do we need for intervals of increasing, decreasing? Well, we need our y prime. So if f is given by that power function, then f prime of x is given by power rule. We've got our 2/3 x squared minus 4 to the 1 less. What's 1 less than 2/3? -1/3. And I was hopeful that you'd be reminded about those exponent type rules during that little connecting derivatives activity. Times the derivative of the base. What's the derivative of the base? 2x. So there we've applied our chain rule with the power rule in order to generate an expression for f prime. And then I could rewrite that so that it's easier to do our analysis. If I combine this looks like 2 times 2 is 4x over, and this looks like 3, and x squared minus 4 to the 1/3 power on bottom. How's that? Single fraction? Great. We know that the only places that f could switch increasing versus decreasing behavior is when f prime is 0 or undefined. So by writing f prime in a fraction form, I just need to consider if this top will ever equal 0, or if the bottom will ever equal 0. If the top equals 0, then y prime equals 0. If the bottom of my fraction equals 0, then y prime is undefined. Those are my only possibilities for y changing direction, and that's why we called them critical points in last class. So, will the top ever equal 0? Boy howdy, 4x set equal to 0 produces the critical value x equals 0. The denominator set equal to 0 through inspection, I get 2 values, right? What 2 values make the denominator equal to 0? Kobe?
Positive, negative 2.
Good. So we've got 1, 2, 3 critical values. So we've got critical values at x equals 0, positive 2, and negative 2. All right. So what's that going to do for me? Well, it'll allow me to do a first derivative number line. The first derivative test, right, allows me to use the sign of f prime to determine the intervals of increasing versus decreasing behavior. Let's go ahead and get our number line here, and we'll label that f prime. On that number line, we'll throw our critical value x values. I've got negative 2, 0, 2. Now I'll choose a convenient x value on each subinterval. Let's choose something that's going to give us a nice number. Can we do that? Are there any nice numbers here? Well, we just need the sign. So if I choose negative 3, the numerator is positive. Is negative. Over, if I choose negative 3, the squaring overwhelms the 4. You see that? 9 minus 4 is a positive. I don't have to know what the cube root of 5 is. I just need to know that the cube root of 5 is positive. And the positive is positive. So I get negative over positive. Overall is negative. That's why the sign test is so nice, because I don't have to get exact values. I just need to know if it's positive versus negative. Convenient x value between negative 2 and 0? Negative 1. Negative 1 makes the top negative. Negative 1 makes the denominator negative, because the 4 is going to overwhelm that 1 and get a negative. Remember, the cube root of a negative number exists and it's negative. Overall, positive value of f prime. Next subinterval, 1. Positive over negative is negative. 3. Positive over positive is positive. All right, so we've already determined our intervals of increasing, decreasing behavior. It looks like f is increasing on negative 2 to 0 and 2 to infinity, because f prime is positive. F is decreasing on negative infinity to negative 2, union 0 to 2, because f prime is negative. Local extrema we needed. So I now need to include, right, those critical values on a number line, and I can determine now my local extrema. When f prime switches from negative to positive, I expect to see a local minimum, because f switches from decreasing to increasing, and vice versa. So what do we need? We need x, f of x. We need negative 2, 0, and 2. And we'll evaluate my original function. Negative 2 squared is 4 minus 4 is 0, so 2/3 is 0. 0 squared is 0 minus 4/3, minus 4 is negative 4 to the 2/3 power. So we're going to have to figure out what negative 4 to the 2/3 power is. For now, I'm going to put negative 4 to the 2/3. So that'd be the cube root of 16. And we're going to approximate that in a minute. And then 2, 0. Awesome. So what have we learned? We've learned that our local extrema at x equals negative 2, we have a local min. At x equals 0, we have a local max. At x equals 2, we have a local min. So let's go ahead and do it. Now, we're trying not to use our graphing calculator until the end to check, but we can certainly get a decimal approximation with the cube root of 16 if it helps our cause. I know we just need a decimal here. So let's do the cube root of 16. just as a decimal on our home screen. So then we get cube root of 16 is about. All right, so, wait, no. So ready? Let's go ahead and make this scale. Got negative 1, 2, 3, 0, 1, 2. This is going to work out nicely. So we'll just go 1, 2, 3, 1, 2, 3, 1, 2, 3, and we get the points. We know we've got negative 2 comma 0, 2 comma 0, 0 comma 2.51. We've got decreasing behavior, increasing behavior, decreasing behavior, horizontal tangent, infinite. Here we had, those came from constant over 0 as infinite value, so I must have cusp. So we've got this type of behavior. And we've got horizontal tangent because that critical value, x equals 0, came from the top equals 0. Can I connect these with a cusp and a horizontal tangent? I think I can. How's that graph? I don't know. Let's do a similar window and check it out. My favorite is always seeing how we did. So we've got x squared minus 4. Tyler, you ought to watch my happy hands here. You know when we start hurrying. And we want a similar window, so negatives 6 to 6. Moment of truth. Do we need to do the salt every time? Okay, we'll do the salt every time. And I even chose blue. Can you believe it? That's not too shabby. Yeah. See if we're good. I'll take it. Hey, that's good news. Let's up the ante. So that was okay. Let's go ahead and include intervals of concavity as well. So we're not going, right, we're not just going to y prime, we're going to go y double prime, baby. Let's go y double prime. So let's determine the intervals of increasing, decreasing, local extrema, and concavity before carefully sketching a graph by hand, and we'll verify graphically. Again, it's okay if we just need a decimal approximation to get a point. We're not using the graphing mode on our calculator, we're just using the home screen. So let's try it out. On 0 to 2 pi, so we've got a closed interval, I need f prime. Go ahead and tell the class what f prime is when I call on you, get ready. So what's my expression for f prime going to be? Riley?
1/2 minus cosine x.
Very nice. And I know that this is defined for all real x because cosine has domain all reals. So we're no problem here. I'm not going to get any critical values from f prime is undefined. However, I'm concerned if f prime equals 0 on my interval 0 to pi. So I'll set this equal to 0 and solve to see if we have any critical values. Those would occur when 1/2 equals cosine of x. And does cosine of x ever equal 1/2 on the interval 0 to 2 pi? You bet your boots it happens twice. So we've got, boom, pi over 3, and boom, 5 pi over 3. Are you guys getting critical values? I'm getting critical values at x equals pi over 3 and 5 pi over 3. Good thing we know we're going to circle forwards, backwards, inside out, in radians, quadrants. Ooh, love it. All right, so what do we do? Well, let's determine our intervals of increasing and decreasing behavior by constructing our f prime number line. We'll label it. We'll get our x values that are critical. That's pi over 3, and we'll cap our interval. So it looks like 0, 2 pi, and in between we've got, what, pi over 3 and 5 pi over 3? Oh, my favorite. So let's go ahead and practice choosing some convenient x values on each subinterval. So what's in between 0 and pi over 3 that's convenient? How about pi over 4? Yes, pi over 4 or pi over 6. Right, either one is fine. We could do, want to do pi over 6?
Yeah.
So pi over 6 would be easiest. So pi over 6 is right in the middle here. F prime, cosine of pi over 6 is root 3 over 2. Root 3 over 2 is about 0.7 divided by 2 is back to pi over 4. Cosine of pi over 4, I know, is root 2 over 2, and that's 0.7, so that's easiest for me. So 0.5 minus 0.7 is negative. Very negative. That's what I want to do. Just because I know root 2 over 2 is 0.7. Convenient x value between pi over 3 and 5 pi over 3. Pi would be easy to evaluate with my derivative. What's the cosine of pi? Negative 1. So 1/2 minus a negative 1, because 1/2 plus a positive 1 is positive. We just need the sign. I'm going to do 7 pi over 4. Cosine of 7 pi over 4 is positive root 2 over 2. That's about 0.7. 1/2 minus 0.7 is negative. Hey, we can do our increasing decreasing just like before. So we know f is increasing on pi over 3 to 5 pi over 3 because f prime is positive. Dot 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 equals a decreasing dot 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 and concavity. So now we're going to differentiate our original f prime to get f double. Riley graciously told us our derivative of f. And now I'm going to go to get our f double prime. So what's our f double prime, Tyler? True that. Cosine differentiates to opposite, so negative cosine of x is going to differentiate to positive sine of x. Defined for all real, so no possible point of inflection from f double prime being undefined. However, we need to see when our f double prime expression equals 0 on my interval 0 to pi. Does that ever happen? Yeah. I've got possible points of inflection at x equals 0, well that's an endpoint, pi and 2 pi. So while I have 0, pi, and 2 pi are all on my interval, 0 and pi are endpoints. So when I go to do my y double prime, or f double prime I should say, I'm going to cap it at my endpoints, so I won't have to do a sign test on either side. Pi is right in the middle. Let's do it. Convenient x value in between 0 and pi. How about pi over 2? Sine of pi over 2 is 1, so that's positive. 3 pi over 2, the sine of 3 pi over 2 is negative 1, so negative. So I've got concave up on 0 to pi because f double prime positive, dot dot dot, concave down, dot dot dot. What do we need? We need some points on our original. So x comma f of x. We're going to include our critical values. We're going to include our endpoint values. We're going to determine our local extremes and our point of inflection values. So what do? We need 0, pi over 3, pi, 5 pi over 3, and 2 pi. Is that all? We'll track. So we need 0, we need 2 pi, we need pi, we need pi over 3, and we need 5 pi over 3. Did I get them all? I'm trying to toggle back and forth between the pages. Let's do it. Where am I putting 0 into the original? I got this. I got this, guys. All right, now you guys do the hard one. So pi over 6 times 1/2 would be pi over 3 times 1/2 would be pi over 6 minus the sign at pi over 3 is root 3 over 2. And I'm just going to leave it like that until I go to Melissa for decimal approximation. Pi, so 1/2 times pi is pi over 2 minus 0 is pi over 2. That's about 1.57. Is that right? 1/2 times pi is pi over 2 minus sine of pi is 0. So it's just that. 5 pi over 3 times 1/2 is 5 pi over 6 minus sine of 5 pi over 3 is negative root 3 over 2. So plus root 3 over 2. And no, it's no problem. It's no problem. It's easy. Ready? 2 pi times 1/2 is 1 pi minus 0 is 1 pi. Is pi is 3.14. Okay, ready? I need decimals. So we need about pretty loud. So we need pi over 6 minus root 3 over 2, Marissa?
Negative 0.342.
And is this right? About?
Yeah.
And
Plus
plus
two.
2. 5 pi over 6 plus root 3 over 2, we need that.
3.48.
Thank you. And pi is about 3.14. I got that. And then we just need to check pi over 2. Is that about 1.57? It's one of those memory things, Sophia? Yes? Let's do it, you guys. So we've got decreasing, increasing, decreasing, and we've got concave up, concave down. I'm putting it all together in my head. Let's do it. So on our axis, 0 to 2 pi. So this is pi over 2, pi, 3 pi over 2, and negative 0.342. Okay, and 1, 2, 3 pi. So we'll just go by ones. How about? Yeah?
Yeah.
Okay, let's do it. Here we go. 0, 0 is an endpoint. We are decreasing concave up until a local minimum at pi over 3 comma negative 0.342. Pi over 3 is going to be right here. Negative 0.342. Grace told us is right here. And that's the local min. I, comma, 1.57. And that is a point of inflection. And 5 pi over 3, 3.48, and that is a local max. Man, we're gonna nail this. I've got a good feeling about this. 5 pi over 3 though is right. 3 point what? 48?
48. Yep.
It's right here. Exactly. And that's our little tangent. And 2 pi, pi. I got that. 2 pi, 3.14. Yes? Can we do it?
Yeah.
Decreasing, horizontal tangent, increasing, point of inflection, concave down, local max, decreasing. Oh yeah.
Yeah.
Stop that endpoint. Stop that endpoint. Moment of truth. I'm going to open a new jar of salt. A new jar of salt. One. Yeah, well, of course. I go big for BC, baby. Minus sine x. Okay. And we want negative pi over 2 to positive pi over 2. Yeah, we're gonna make it. No problem. Oh yeah. You don't think we're gonna make it?
I'm worried.
It's gonna be just right. So here we go. Down, local min, point of inflection,
We nailed it.
and how do we do?
Perfect.
Huh? That's pretty well. We did pretty well. Awesome. So you might be thinking right now, how in the world are we going to do all this? Well, we'll do that next time.
Yay!
Why not? If y double prime equals 0 or is undefined at x equals c, then y has an inflection point. True or false? Don't say it out loud. Now complete your statement. Y has a critical point when y prime. Y has a relative minimum when y prime. Y has an inflection point when y double prime. Oh gosh, this is good. I like this one. Okay, true or false? If y double prime equals 0 or is undefined at x equals c, then y has an inflection point. So what did you guys come up with for that one? Riley?
False.
False? What's wrong with that?
There's more to it.
There's more to it. Right? There's more to it. What has to occur in order for y to have an inflection point? Yeah, y double prime's got to change sign. So it's not enough for y double prime to equal 0 or be undefined. That's simply a possible point of inflection. We need to, it warrants further investigation. And I hope we got that from your activity. 2, y is a critical point when, what's true about y prime? Courtney?
Equals 0 or something.
Good. So equal, oh my gosh. That's not going to work. That's not PDFable. When y prime equals 0 or is undefined. Thank you. Go ahead and share your response to number 3. When I call on you, y has a relative minimum when y prime. Emily?
Is negative?
Let's see. So y has a relative minimum when y prime. So y prime negative.
Which is from negative to positive.
Absolutely. When y prime switches from negative to positive. Good. And one to go. Y has an inflection point then when y double prime, Kobe, changes sign. Nice job, and that's why we have to do our number line. Way to go, you guys. Nice work. So what's up? Well, we've got our OTL number 2. Most of them are odds, but there's a couple of evens. Strong work today.